Welcome to another exciting video brought to you by Vision Concept Academy. In this video, we'll be looking at capacitors and capacitance. A capacitor is a device basically used for storing electric charges. It consists essentially of two capacitor metal plates carrying opposite charges. Metal plates are separated using a small distance by an insulator. The insulating material between the plates of a capacitor is called a dielectric substance. The capacitance increases with the area between the plates, decreases with increasing distance, and increases with dielectric constant. So this is the symbol of the capacitor. Like I said in the introduction, it is represented by two metallic plates like this, and then the distance between the two of them is known as D. The distance between the two of them. It's a material at the center known as the dielectric. That's the symbol. This is the symbol. I'll just see it as symbol. But if I want to draw the diagram, I'll draw it like this. You have the circuit going here. Let me just put the metal plates, the plates like this. This is how it looks like. Okay, it's capacitor. Okay, so at the center, I will have a material that will fill. Let me just color this. It's a material in between them like this. So this is Q1, sorry, Q positive and Q negative are the charges. So you have, this is known as the metal plate. This is the metal plate. Okay, what else? So of course, I have a cell powering it like this. Forget about the whole thing. Then this is the distance of separation D. Okay, so this material is shaded in. I'll just put my arrow here. Is an insulator. It's not a conducting material. So this insulator is the one that's providing the dielectric. Then you have the metal plates. This is a metal plate. This is a metal plate. Okay, so this is how it looks like. Now there's a concept known as capacitance of the capacitor. So the capacitance of the capacitor is defined as the ratio between the charge Q on either plates or conductors to the potential difference. So capacitance, okay, is the ratio of the charge to the potential difference. Is the ratio of the charge to the potential difference. No, remember that charge is measured in coulombs. In coulombs. So quantity of charge, quantity of electricity is measured in coulombs, and the V is quantity, and V is the potential difference. Potential difference measured in what? In volts. Okay, so that's the capacitor, the ratio between the quantity of charge and the potential difference. So the unit of capacitance is the farads. Unit of capacitance is farad. You have other units. You have microfarads and picofarad. So 1 microfarad like this, micro, of course, this is micro. 1 microfarad, that is 1 mu f, is equals to 10 to the power 6. Of course, it's minus 6. Minus 6 farad. Okay, and 1 picofarad. I hope you can see this. Let me go up a little bit. Unit of capacitance is farad. Okay, let me take this off. So unit of capacitance is farad. So 1 microfarad will give me 10 to the power minus 6 farad, and 1 picofarad will give me 10 to the power minus 9 farad. So these are the units of farad. This is not, this is 12, sorry. Okay, so these are the units, so be familiar with it. Quantitatively, the capacitance of the capacitor is ability to store up electricity. Okay, so we'll just take some questions and or just one question. Then we'll look at the arrangement of capacitors, that is in series and in parallel. So quickly, they said a capacitor of charge of charge um, 5 times 10 raised to the power minus 6 coulomb has potential difference of what? Of 10 volts. What is the capacitance of the capacitor? So this is a simple application of what I just said. What is the capacitance of the capacitor? Okay, just like as you have the resistance of the resistor. So you have the capacitance of the capacitor. Okay, so you know I told the capacitance C is equals to what? Q over V. And the charge given here as 5 times 10 to the power minus 6, and the potential difference is given as 100. By the time you compute this, I have capacitance of the capacitor as 5 times 10 to the power minus 4 farad. So this is the capacitance of the capacitor. 5 times 10 to the power. Okay, sorry, this is in the question is given as 8. Let's use what's in the question, 8. So if this is 8, this one will be 12. Because by the time this 2 goes up as negative, it becomes, is it 12? It becomes 10. It becomes 10, yes, I'm right, 10 farads. Okay, so this is just it. And if you convert this one now to microfarad, what do we get? Microfarad. We get 5 times 10 to the power minus 4 microfarad. Microfarad. Why? Because you just divide this one by this. When you do so, you get this. That's a microfarad. Most of the rating of capacitors in the market is a microfarad. Okay, so we go into the arrangement of capacitors in series and parallel. Okay, so here we have arrangement of capacitors in series and in parallel. So this is capacitor in series and parallel. Remember when we talked about resistors and we saw that it's almost the same kind of arrangement for the two of them in the diagram form. For capacitors in series, they are connected in a daisy chain form. That is in to in a daisy chain form. Like for in parallel, you see that it's connected across, voltage applied across the terminal, and each capacitors are connected uh, uh, up and down, up and down. You understand? Okay, so now there is the concept of equivalent capacitance, or resultant capacitance, or net capacitance, or total capacitance. For capacitor in series, total capacitance 1 over C, where C here is the total capacitance, is equals to 1 over C1 plus 1 over C2 plus 1 over C3. That is how you get capacitors in series. But in parallel, C is equals to C1 plus C2 plus C3. Note that this is like opposite of what we did in the resistance, where the series is computed like this, total resistance computed by addition, just summation of the individual capacitance or summation of individual resistance. That's for the case of the resistors. And for the parallel connection, it is like the uh, uh, sum of the reciprocal of each of them. You understand? So, but it's opposite in capacitance. Okay. All right. So note that difference. Note that difference. So the resultant or equivalent capacitance of any number of capacitors connected in parallel is the sum of the individual capacitance. Okay. The reciprocal of the equivalent capacitance of any number of capacitors connected in series is the sum of the reciprocal of the individual capacitances. Okay, so I have on the board an example we'll just look at. It says two capacitors of capacitance 5 microfarad and 3 microfarad are connected in series, and the resultant combination is connected across a 600 volts. What is the equivalent capacitance of the combination and the total charge on the combination? By diagram, I have two capacitors like this in series, and they are connected across 600 volts. 600 volts, and this one is 5 microfarad, and this one is 3 microfarad. The question 1 says we should calculate what equivalent capacitance. Since it's in series, it's 1 over C is equals to 1 over 5 plus 1 over 3. So this is what our equivalent capacitance is. So by the time we compute the two of them, 1 over C is equals to this 1 over 5 plus 1 over 3 will give us 8 over 15. Sorry, 8 over 15, and C is equals to 15 over 8, and C will give us 1.875 microfarad. 1.875 microfarad. 1.875 microfarad, because this is already microfarad. Okay, so we have gotten C, the equivalent capacitance, just adding it. So what I'm testing you here is to know whether you know the formula for series connection of capacitance. If it's a parallel connection, you just simply add it, 5 plus 3, 8. But because the connection is in series, you apply this formula. So that's the test you have tested in this number I. So for II, we're told to find the total charge. Remember, we define capacitance again as charge over potential difference, right? We define capacitance as charge over potential difference. Sorry, no, not that. Just hold on a second. Okay, so on total charge, Q is equals to CV. Q is equals to CV, where C is the equivalent capacitance already given in the I above as 1.875 microfarad is 10 minus 6, 10 to the power minus 6, then times the voltage of 600. So the answer for the charge in Coulomb is 1.125 times 10 to the power minus 3 Coulomb. So that is the charge. That's the charge on the combination. Okay. Okay, so we're told to find the equivalent capacitance of this capacitor's connection. Now, there are two kinds of connection here. This and this are parallel connection. When you find the resultant or the equivalent capacitance of these two of them, what you have as a resultant is in series with this one. So you are being tested by identifying the arrangement, the kinds of connection we have. So first of all, we are going to be resolving the parallel connection. For parallel capacitance, equivalent capacitance for parallel connection, C is equals to C1 plus C2. So in this case, parallel, C is equals to 3 plus 2, which is equals to 5. So 5 here represents, I'll just put it here. So this 5 is not in parallel in series with this. So for this one now, I will now say 1 over C is equals to 1 over 5 plus 1 over 4. I hope you understand what it is. There are two connections. This first one is the parallel connection. It has been done. When you get the resultant, you use it as a series to this one. The resultant of these two is now in series with this one. So the series formula is you have this fractional case, you find the LCM. The LCM of 5 and 4 is 20. So 5 into 20 divided by 5 is 4. 4 times 1 is 4 plus 5, yes? So 1 over C. So 1 over C is equals to 9 over 20. Then C is equals to 20 over 9. So this is the total capacitance, microfarad, of that connection. Or you can leave it in fractional form like this, or you call it 2.22 microfarad. So we have on the board energy stored in a capacitor. So a capacitor is charged so that it can store any electrical energy. While the capacitor is charged, the charge builds up, from an initial value of 0 up to you get to the final value of maybe Q, and the potential difference between the plates builds up from 0 to final value of V. Okay, so during this charging of the capacitor, the average value of potential difference is given by that is from 0 plus V over 2. So it builds from 0 to V over 2. So it now becomes 1 over 2V. 1 over 2V, yes. 1 over 2V. This is the average value of the potential difference. That is when it's starting from 0 and builds to the final value. So the work done in charging the capacitor through an average potential difference of this is given as W, where W is work, is equals to 1 over 2V, then times Q. Okay, so in this case, this is the charge and this is the average voltage that is built up. But we know that C is given as Q over V. If this is true, or again, V is given as Q over C. That is just by making the generator formula. Therefore, W, this one, I can have it here as, I can say 1 over 2. This V now becomes Q over C dot V, dot Q, sorry. So I'm writing this one in terms of this. So W is equals to 1 over 2 Q squared over C. So this is a way of expressing the work done. And even if we put Q is equals to CV from here, remember, if we say Q is equals to CV, right? We can still say work done is equals to 1 over 2 V dot CV. W is equals to 1 over 2 CV squared. This is another way of expressing work done. Work done. Okay, so work done has many expressions. It has this one. This one is one of them. This one is one of them. Followed by this one and this one. There are 3 of them. So I can call this one 1, 2, and 3. These are the 3 ways we can express work done. And we know that the unit for work, W, is joules. Remember that Q is in coulombs and V is in voltage. So the work done in charging the capacitor is the energy stored in that capacitor.